Hello, this is the correction of the paper of June 19, paper 33. So the question is about how sodium thiosulfate reacts with H+, giving rise to sulfur and sulfur dioxide and water. The sulfur form here is a white solid or a yellow solid, and it masks any printed insert which is found below it. Now, usually what you have to do in an exam is to place the mixture in a beaker and to place the beaker on a printed insert which will be provided at the time of the exam. So let's assume that you have a printed insert that we have, for example, a cross on it. Then the mixture that you pour here is going to react, and as time goes by will become white. And by the time it becomes white, it is difficult for us to see what is written on that printed insert. And that lapse of time, you are going to take it using a stopwatch. You're going to count it, and that time taken now is referred as your reaction time. Of course, the rate of the reaction can then be calculated by taking the inverse of that reaction time. So that is how the practical should be done. You need to use some equipment which is provided there, using a burette to measure Fa1 and using a measuring cylinder to measure Fa2, and using at about Fa2 and Fa1 in the beaker, and start timing immediately. So the procedure, I hope it's okay. You follow the procedure properly and you should be able to do the practical. From the experimental results that we have here for one candidate, it's very important that you measure and you insert it there correct to 2 decimal place and to the nearest 0.05, because the measurement was done using a burette. So remember that burette readings should be nearest 0.05 centimeter cube. Now, it's very important to plug centimeter cube and not milliliters. Beware about it. Cambridge is not accepting milliliters as an answer there. It's not accepting milliliters. So milliliter is a mistake. You have to take centimeter cube. Now, in that practical, water was measured using a cylinder. So the value could have been written to the nearest whole number. So the value of water here, that can be to the nearest centimeter cube. Like, for example, 10 would be okay instead of 10.0. The time was noted using a stopwatch, and time should be noted every time using to the nearest second. So remember this. If a candidate is writing 73.5, for example, this would be a mistake. Time should be to the nearest second. During the practical here, the total volume should be kept constant. So that total volume here should be constant. This is very important. Now, as you can see, the candidate varied here the volume of Fa1. By varying volume of Fa1 becomes our independent variable. The candidate also keeps a volume of Fa2 constant. By keeping volume of Fa2 constant, that becomes a control in that practical. You can also refer to the total volume being a control because it is kept constant at 55 centimeter cube. Now you need to keep total volume constant to make sure. This is a very important feature. It came in many exam papers. Why should we keep the total volume constant? So you keep total volume constant, constant, so that the change in concentration is proportional to a change in volume. So as a homework, you can go and prove why is it that when we keep total volume constant, a change in concentration becomes a change in volume. Otherwise, if let's say we take the value, let's assume that we take the value 20 and we take the value 45. If we don't keep total volume constant, then does it mean that by changing 20 to 45, the increase in that concentration would be the same increase in the would be proportional to the increase in the volume? It doesn't mean this. So by keeping total volume constant, we can calculate the factor by which the concentration increased. The factor is, so concentration factor is 45 over 20. That concentration factor would be the same as the volume factor, or that volume factor would be the same as the concentration factor, right? So it's important to keep this in mind. And in that table, you can see that the candidate has here the rate written as 1 over time. Now, it's very important to have the unit of second minus 1 because the reaction times were noted in the nearest second. So that is for the first part. Now, from this, if we go back again, you can see there that Cambridge asks you to point out any anomalous point. Now, this is optional. You can have or you can still not have any anomalous point, but if there is any coordinate which is outside the graph, you need to show it. It's important. So then we have a plot, and that plot was okay. So every time you do a plot, make sure that you label the axes. So the candidate label the FA1 there and the axis, labeling here the rate and the axis again, and starting the labeling of the origin or starting the labeling of 15 and 6. Now, as you can see, there is an anomalous point here that the candidate showed. That is very important. A line of best fit now can be a straight line. So note this carefully. When we say a line of best fit, we can have a straight line or we can have a curve. So you need to be careful. Either Cambridge would say a straight line of best fit or a line of best fit. In the case of a line of best fit, that could be a straight line or a curve. But if it says a line of best fit, then but if it says a straight line, then you need to draw a straight line. In that question, if we go back there, label on the grid, plot a graph against this label, draw a line of best fit. So you can draw a line or you can draw a curve. That is up to you. You go and choose. Now for this one, it appears clearly that a line can be drawn that passes through the points. Look carefully how the points are on the two sides of the line. So 1, 2, 3, 4. That is a very good way, a very correct way of drawing a line, so that the coordinates are equally distributed on the sides of the line. Now, it's also important to note that when you draw, always draw with a cross and not with a dot or a dot in a circle. Now that is from Cambridge. You can see what I'm saying here. You can look at the proof in the book of Ryan and Norris. On the page where it talks about experimental details. So Cambridge likes to have a cross instead of a dot or a dot and a circle. Now, the reason behind is difficult to argue, but I think that it is because the paper would have to be scanned for correction, and it is easier to scan a cross than to scan a dot. So if you have a single dot, it's difficult to scan it. Again, this is my perception. I don't know why Cambridge would prefer a cross, but I have this feeling that the cross is preferred by Cambridge because of the scanning. So that was a good graph. For the next one now, in this experiment, the volume of Fe1 is related to concentration. As we can see, a straight line was obtained, so that was a good answer to say that the reaction is directly proportional to the concentration, or anything in this form will give you a correct answer. Any reason showing that there is a proportionality between the concentration and the rate. Any answer in this form would give you a full mark. Part D, calculate the minimum value for the reaction rate. Now, if you are looking for minimum value for reaction rate, you are going to look for maximum reaction time, as the candidate pointed out clearly there, maximum reaction time. So that was very good. So from the table, the maximum reaction time was 73 seconds. That's why she added a value of 2 there for the +2 and calculated the minimum rate to be 6.67. Minimum rate, I think that I said maximum rate some few minutes. It was maximum reaction time for looking for minimum rate. Discuss whether the student is correct. Look at this question. So instead of using a 250 centimeter cube, the time recorded would be the same. Yes, in that practical, the candidate did it in a 100 centimeter cube container, beaker. Now, you are changing a 100 centimeter cube to a 250 centimeter cube. The thing is that you have a larger cross-sectional area. So this is a 100 centimeter cube container, and this is a 250 centimeter cube container. Now, if you look in a cross-sectional area, this cross-sectional area of this beaker, now you have to you need to try to see the diagram. I'm not too good in drawing. So this is our 250 centimeter cube. You can see that this cross-sectional area is much more. So what happened is that the height of the solution would be less. So for the same volume, of course, the volume, the total volume, I think it was 55. So for the same volume, the height is going to be less, and less light is going to be absorbed, and it will therefore take more time to be opaque, to obscure the marking there or the printed insert. So the time taken would be more. And the candidate wrote it there, the time recorded would be greater as the depth of the solution would be less, and the printed material would take more time to disappear. Part ED now, second part, a student carried out a further experiment using the same procedure. The student used 5 centimeter cube of Fe1, 40 of distilled water, and 10 centimeter cube of Fe2. The printed on the insert never became visible. This is because the 5 centimeter cube here is too little amount of Fe1, and the amount of sulfur form is not enough to obscure that printed insert. So too little concentration, the time is very, very long, and it has a lot of error. So I would say that if ever you have to choose a volume to use in such a practical, always choose a volume which is bigger than 10 centimeter cube. And usually you are provided with some forms of experimental faster reaction or slow reaction. So you are asked to perform the reaction where Cambridge is going to tell you which volume to use, and you are to choose for yourself the remaining volumes. So if you are to choose, don't choose a volume which is too low, because the judgment error in those volumes is very large. You know that judgment error error is the error that you have when you are to judge when the color becomes opaque or when the color is actually sufficiently opaque. When the concentration is high, that judgment error is very low because the solution becomes opaque immediately. When the concentration is low, that judgment error is very, very high because you have a difficulty to decide when to stop the stopwatch or when you feel that the color is opaque or not. So always use high concentration as far as possible, and to have high concentration, always use large volumes. You have in them less judgment error, right? So you have less judgment error in it. So that is for question number 1. Let's look at question number 2. Question number 2, we have a question on Fe3, which is sodium thiosulfate, that it says there. And we are to look for the enthalpy change of solution. So we are going to take a beaker, a polystyrene cup this time, in which we are, so let's draw a polystyrene cup property, that is a beaker. So we take a polystyrene cup, that is better. And in that polystyrene cup, we're going to measure a certain mass of sodium thiosulfate, and then we are going to add a water in it, right? We add water in it, and we are going to measure the rise in the temperature or the drop in the temperature by using a thermometer. So that was the practical part. It was fairly easy. So remember, when you draw a table having mass, insert them correct to the number of decimal places that you have in your balance. For my balance, it was 2 decimal places. That's why the candidate had a value of 0.63. If you got a balance having 3 decimal places, you need to insert them. Now, you need to keep consistency between those decimal places, you see? So every time the candidate took 2 dp and 2 dp. And not 1 2 dp and the second time 1 dp. You will lose mark on the accuracy. Like, for example, 55.6 and then 75.6 and then 71.69 and then 3. And then 3. So these are not consistent at all. You're going to lose mark for this. So you should not be doing it. So the candidate did it properly there by keeping consistency in the results, and as you can see now, temperature should be quoted every time to the nearest 0.5 degrees. That was properly quoted again there. So the accuracy was okay. So nearest 0.5 degrees Celsius for temperature reading, and 2 dp or 3 dp for mass reading, and always keep consistency. So that was properly written there. Calculate how many moles of Fe3. Question number B1. Calculate how many moles of Fe3 were added to the beaker. So that was a mass. Number of mole is obtained as the mass divided by the mR. That was done properly there. 3.94 for the mass divided by the mR. Next one, calculate the heat energy. So that is a very important part. Whenever you use heat energy, whenever you are to calculate heat energy, most of you use an equation. And there's only one equation which is accepted by Cambridge, and that is delta H equals to minus mc delta T. And you can see there the candidate used theta. So that theta is not accepted by Cambridge, unfortunately. So you need to be careful about it. Use the proper equation, and that equation figures in your syllabus. You can check it. You will see it in your syllabus. Another thing in that equation is that M stands for volume, total volume. It never stands for mass. So that is the total volume, and C stands for the heat capacity of water. So it's the specific heat capacity of water. So one way to remember that is, and that M stands for volume, is you cannot plug in an equation heat capacity of water, which is 4.2 joule, and then you plug in the same equation the mass of something. It is not possible. So if you are plugging the heat capacity of water, it has to be the volume of water. And in that equation, in that question, we assume that the solution is so dilute that the solution is having the same capacity as that of water. So that you should take into picture. You should bear in mind that in that equation it is always volume. Even though if we have 100 centimeter cube of a solution, let's say 100 centimeter cube of HCl mixed with 2 grams of calcium carbonate, the V would be 100, and it won't be 102, or it won't be 2 gram. So, 102 is wrong. So let us put this as it won't be 102. So that would be wrong. It won't be 2 also, which would be wrong. So the only answer that we're waiting there is 100. So remember that M stands for V, which stands for the total volume. In that case, it was properly calculated. Another thing that I have seen in the past is many of you have a difficulty to choose the unit. Which unit do I place here? Is it joule or kilojoule? It's very easy. The question gives it. Look at this, 4.2 joule. So if you plug joule in that equation, then you should end up having the answer in joules, right? Calculate the enthalpy change of Fe3, so that you calculate for 1 mole. In the previous part, you calculated so many moles of sodium thiosulfate, so for 1 mole, it is the answer above divided by that number of mole. One way to improve this experiment would be to use a balance that read more than 2 decimal places. So there's 2 other ways. There are many ways by, for example, using a larger mass. Now, you need to know that when you use a larger mass, the percentage error is less, because percentage error is n times the absolute error divided by the value measured multiplied by 100. And if you increase the value measure, the percentage error drops down. That is a mathematical fact. So using a larger mass, you have a less error in the practical. Using a digital thermometer can also be correct, because you're going to have more precise temperature reading. You can also use more accurate apparatus like burette. You can also say lagging the container, preventing the heat loss. Place a lid. You need to be careful when you place a lid. You prevent 2 things: either escape of heat or intake of heat. Escape of heat or intake of heat. Intake of heat means that if the reaction is exothermic, so you have escape of heat, you place a lid to prevent heat from escaping. If the reaction is endothermic, you need to be careful. Don't ever say that the reaction was endothermic, so preventing the loss of heat, that is a mistake. So you place a lid in an endothermic process to prevent heat from entering the solution, not from escaping. So bear this in mind. In some endothermic process, I have seen in the past student writing place a lid, and the reason was to prevent the loss of heat. That was a mistake. So you place a lid for an endothermic to prevent the absorption of heat from the surrounding. Question number D. A student carrying out the experiment in question 1 used all the Fe1. The student make up a sample of Fe1 of the correct concentration by dissolving an amount of Fe3 in water. This solution was then immediately used to repeat the experiment in question 1, but the time was much greater. So why is it that if we prepare the sodium thiosulfate, sodium thiosulfate and then we perform experiment in question 1, it takes more time? This is because the dissolution of thiosulfate is endothermic. So the temperature is low, and when temperature is low, rate also is low. Right? That's why it took more time. Fe3 contains water of crystallization? No. So that is a wrong answer. So because the reaction was endo, the temperature was low, and therefore the rate was very low, or the rate of reaction was slow. If you want, you can also explain in terms of frequency of full collision occurring per unit time. That also you can explain. Again, you have a low rate, right? And it is slow. So that is for question number 2. Let's look at question number 3 now. That was a question on salt analysis. Some few things, whenever you have a salt analysis, don't forget that if you have a gas, if you got a gas, you need to test the gas. And there are many testing devices that are available in your lab to test them. But we can easily see gases like carbon dioxide. These usually they come with brisk or rapid effervescence. Sulfur dioxide is a choking gas, so you can have effervescence. It's usually not so brisk, but we have effervescence, but we can test them using potassium manganate paper. So you take a piece of paper, you dip it in acidified potassium manganate, and the gas will change the color from purple to colorless. For the carbon dioxide, it would be brisk effervescence, and we can test with lime water. But usually the brisk effervescence is enough to tell you the presence of carbon dioxide. Of course, hydrogen gas will burn with a pop sound, oxygen will light a glowing splint. One very important thing is whenever you have the formation of NO2 by the decomposition of salt, it is always accompanied with O2. So remember, if you see a brown fumes when you're heating a solid, then the brown fumes is accompanied with O2. So you need to say that a brown fume has been was observed, and a gas that relies a glowing splint, even though you do or you don't test it. So you need to mark it there. You need to mention it. So in that case, Fe4 was either a solution containing a single cation and a single anion, containing a single cation and single anion. This was sulfate or sulfide, so that was very easy. When we add sodium carbonate in it, there was a rapid effervescence. Of course, there was a gas, and because it was sodium carbonate, the gas was carbon dioxide, and you need to write the test. So it turns lime water milky. So 1 mark will be deducted there because of not writing the test of the gas. How do you know whether it is sulfate or sulfide? It's easy now. You add barium chloride followed by nitric acid. Of course, you get a white precipitate which is insoluble, telling you that it is sulfate. But the formula was sulfuric acid, H2SO4. How do we come to know? Because we have effervescence with this sodium carbonate, we have 4 possibilities. But out of them, 1 is correct there because it was a solution. So 1 possibility is that it was H+. So 1 possibility, H+ gives you effervescence with sodium carbonate. There are a few more things that would give you effervescence. Those highly charged cation, Fe3, Cr3+, and Al3+. But of course, they would also give you white precipitates. Because the solution was colorless, it was H+ there. Right? The next part now, a small spatula of Fe5 in a hard glass tube. Heat the sample gently at first, and then, of course, the blue color there, according to that candidate, changed into a black. There was also a gas, and the gas was again carbon dioxide, and the test should be written there. The second part, to the black solid there, we add a small amount of acid. So you got effervescence, a gas was turning lime water milky. That was not turning lime water milky, and the solution becomes blue actually. So a blue solution was obtained, blue solution formed. To that blue solution, we add sodium hydroxide. They got a pale blue solution insoluble, and then we add ammonia. There is a pale blue precipitate that is soluble to give a dark blue solution. So these are very easy observation to tell you that Cu2+ was present. This is a very easy observation to tell you that carbonate was present. So that is how we come to know in part 3 here that the cation is copper and carbonate, the anion. What type of reaction was reaction 1? So when we are heating, we are decomposing. So that's why decomposition there. Right? So one more thing that I would like to say is whenever you test for barium, let's go back again. This was the test for barium. So you can write barium chloride, you can write followed by HCl, you can write barium nitrate, followed by nitric acid. This is also a variable allowed, but you are not allowed to write barium ions followed by acids. So that is wrong. It's very easy why it is wrong. It's easy to understand why it is wrong, because barium ions can also stand for barium sulfate, and we are not foolish enough to add barium sulfate to test for sulfate. So you see why candidates writing barium ions there would make a mistake, would do it wrong. So be careful about it. Write barium chloride or barium nitrate and not barium ions.